Very good evening to one and all, and especially to Professor Basudeb Dasgupta from TIFR Mumbai, who has joined us today to deliver his special public webinar on the topic The Impossible Dream of Neutrino Astronomy. This special public webinar is part of the school outreach program, which is jointly organized by the National Academy of Sciences India Delhi chapter and Deen Dayal Upadhyay College, University of Delhi, under the aegis of the DBT Star College program. This is the fourth webinar in a series of, it's a 3 months program. And I'm really thankful to Professor Anurag Sharma, chairman of the NASI Delhi chapter, Professor Ajoy Gatak, president NASI, who helped me in conceptualizing this whole program. And a special thanks to all the students, the school teachers, and the principals who have been part of this journey and who shall be part of this journey for the next 1 year or so. So before inviting Professor Dasgupta, let me briefly introduce him to attendees. Professor Basudeb Dasgupta is a theoretical physicist at Tata Institute of Fundamental Research, that is TIFR Mumbai. He studies astroparticle physics, which is the interplay of particle physics, astrophysics, and cosmology. For his significant contributions to neutrino and dark matter physics, he was awarded the ICTP prize in 2019. With this brief introduction, now I invite Professor Dasgupta to kindly share his screen and deliver his talk. And I request all the attendees to kindly type their questions or queries in the chat section. Over to you, Professor Dasgupta.
Thank you for the invitation, and thank you for this lovely opportunity to talk to all of you. In particular, I would really like to thank Professor Saxena for this wonderful initiative. It brings us closer together to school children and our younger members of the scientific community. I'm really glad to have this opportunity to tell you a little bit about something that I'm very excited about. Okay, so the topic today is the impossible dream of neutrino astronomy. So I will tell you why this is an impossible dream, why it was thought that it was impossible to do astronomy with neutrinos. And since I'm talking about it, and very happily, you might guess that this impossible dream hasn't remained impossible. It is a possible dream after all, but the fact that it was thought to be impossible demonstrates human ingenuity and how far we have come. Okay, so we begin. Right. So some of the questions that have puzzled humans have remained the same for millennia, for thousands of years. We have been asking the same questions. For example, this is a little excerpt from the Rigveda, and here this part of the Rigveda asks, how did the universe form, and who really knows, who will tell us, and where was all of this created? And then at the end, it says something very interesting, which is that the gods came afterwards with the creation of the universe. So you see, even at that time, they are realizing that their notion of whatever gods were, it is secondary to the notion or the idea that the universe exists. So the universe is somehow even more fundamental than their notion of God. And they're not saying that, well, the gods know how the universe existed because the gods came afterwards. So this is just one of the places in very old literature from thousands of years ago But humans have been asking these very fundamental questions, that what is the universe made of, where has all of this come from, and so on. We immediately move on to something a little bit more understandable to us modern scientists. So here are 4 examples from very different parts of the world. So top left is a tablet. These are mud tablets, like rectangular tablets. And you can see there are these lines on them. That's text. So they have written something there using a little stencil. So it's like a little piece of bamboo or some stick, and then they poke the mud to write. And what's written here in 164, before the beginning of the Common Era. We used to say before Christ, but that's very religious. So we now use a more secular language. BCE means before Common Era, meaning in what we would have called before Christ. Now we say before Common Era. Common Era begins, 0 is Common Era, is the beginning. So this is 164 years before the beginning of the Common Era. And already at that time, the Babylonians, so this is nearby Iraq today, they were talking about Halley's Comet. I think most of you have heard about Halley's Comet. It comes repeatedly around Earth. And so they were talking about Halley's Comet. So they had realized that there are these stars that appear in the sky and then they go away. Of course, these are not stars. We now know that these are comets. Similarly, a bit later, 60 to 100 years before the beginning of Common Era, this is what is called the Antikythera Mechanism. So it's a little machine made of wheels and gears and so on, which was found off the coast of an island in Greece. The island is called Antikythera. So there are 2 islands, Kythera and Antikythera, and this was found off the coast of this island, Antikythera. And for the most part, it wasn't understood what this machine does. But over the years, people have made guesses, and it appears that this was used to make predictions about movements of stars. So they had made this machine, which allowed them, you rotate the different wheels, and based on the rotation of dials, just like a watch, you can then predict the motion of, let's say, planets or stars or what have you. The third thing, the bottom left one, is a little shloka written by Aryabhata. And while I can't read it and I don't know what exactly is written here, this is from a book by one of our famous mathematicians here in India. And what it does is it gives you a way to calculate what we modern scientists or mathematicians recognize as the sine function. So in school, you must be doing trigonometry with sine theta, cos theta, and we know how the values of sine for simple angles. Like sine of 30 degrees is half or something, right? So, but what about sine of 27 degrees or sine of 19 degrees? This is a bit hard to compute, and perhaps many of you who are in school may not even know how to compute it. This was only discovered by Western scientists, like many years later. So I would say in the 1800s or so, 1800s, 1900s. And interestingly, in India, we had a very reliable, very accurate way of calculating these trigonometric functions already in 600 of Common Era, which would have normally been called 600 Anno Domini or after Christ. So 600 Common Era. Similarly, 700 Common Era, this is a star map. It's like one of those maps of the sky that you would be shown in a planetarium. But this is drawn on paper, I think, and this is from China. And you might even recognize some of the familiar constellations. So for example, here is our, very familiar Saptarshi Mandal. Okay, so clearly, very ancient people, more than 1500, more than 2000 years ago, they were thinking about the skies, and they were excited about what they see in the sky. And this excitement has not gone away. This excitement has continued, and we continue to be excited about the things that appear in the sky. In the Middle Ages, after some of this information from these ancient cultures in India and China went to modern day Arabia, and then from there on to modern day Europe, one of the biggest things that happens was the invention of the telescope. The invention of the telescope by Galileo, and you see a painting of Galileo showing his telescope to the Duke. It's like the local chief of Venice, and this is this painting by the famous painter Bertini. And in the bottom, in the middle, you see a telescope of Galileo. I'm not sure if it's a replica or a real one, but what have you. On the right, however, you see something even more interesting, a little glimpse into how science is really done. This is a page from Galileo's diary. And at the bottom, if you see, there are these 4 asterisks that are being shown near this circle with the crosses in them. The big circle with the crosses is Jupiter, and those stars are the moons of Jupiter. So with his telescope, Galileo was seeing the moons of Jupiter and making diagrams of how these moons move around. For example, here you can see that one of the moons is on the left of Jupiter and 3 of them are on the right. At some later date, he sees all the 4 moons towards the bottom left of Jupiter and so on. So Middle Ages, with the availability of a telescope, Galileo is looking at the moons of Jupiter. This continued, and one of the biggest advances in modern day science and which would lead to bigger advances in astronomy was the understanding of light. If you understand what light is, you can manipulate it. And Isaac Newton wrote his very important book about the nature of light and what you could do with light. And people learned how to use lenses and mirrors in a more efficient, how to use lenses and mirrors in better ways and prisms to make better quality telescopes. However, Newton's understanding of light wasn't quite correct. He thought that light was made of tiny particles that travel just like a cricket ball would do if you throw from one place to another. One of his contemporaries, perhaps Christian Huygens, worried that light wasn't quite like a particle, but instead it was a wave, like the waves you see on water. And this controversy remained for a while. In fact, because Newton was, of course, one of the greatest scientists of all times, Newton's idea was thought to be, it was very predominant until there were experiments in the 1800s, the Young's double slit experiment that some of you in your 11th and 12th that you might have read about, the Young's double slit experiment. The idea is that you make a screen and you make 2 holes in it, and you make another screen with only 1 hole in it. And you put this 1-hole screen behind the 2-hole screen, and the light is behind the 1-hole screen. And you have to use a specific kind of light. And then what happens is that the light that is emitted from these 2 tiny holes in the screen, they're allowed to fall on some white colored, nice clean screen on another side. And what you see is not uniform illumination. It's not like turning on 2 light bulbs in the room and you see more light and that's all. What is seen is something really remarkable, is that the light from the 2 independent slits or sources that they can both add and subtract. So in some places, the light interferes negatively or destructively, and it creates more darkness than what you would have with just one source. And in some places, the light adds constructively, and you have not just twice the amount of light, but maybe 4 times the amount of light. So this is called interference, this pattern of light and dark that is created by the superposition of light from 2 coherent sources. And this was one of the defining experiments that gave support to the idea that light is a wave. And it took another 100 years or so to develop detailed understanding of light as a wave. Maxwell and Hertz and others developed this understanding that light is nothing but oscillating electric and magnetic fields, okay, which are transverse at 90 degrees. And then there's a wave that travels perpendicular to both the electric and the magnetic fields, and that's light. So light was understood as an electromagnetic wave. Now we know that this light comes in many different kinds, or to be more precise, many different frequencies or wavelengths. Okay? So light is a transverse electromagnetic wave, but it can have many different frequencies or wavelengths. And what you see here in this slide is an illustration of the different kinds of light, the different frequencies of light. This on the top tells you the wavelength of light in units of meters. So human beings are about, a meter in size. So 10 to the 0 is 1 meter. 10 to the 3 meters is a kilometer. That's here. And then on the right-hand side, these are smaller wavelengths leading all the way to 10 to the minus 12 meters, okay, which is roughly the size of an atomic nuclei. So that's a Fermi, a femtometer. Okay. And at all these different wavelengths, light has slightly different character. For example, the light, which has the wavelength roughly comparable to size of human beings, a meter or larger, these are radio waves. These are radio waves, and they have the property that they can bend around obstacles which are approximately a meter or 10 meters in size. This is the reason why you can run a transistor radio without worrying about whether it has line of sight visibility of the source, the antenna that is creating the radio waves in the first place. Somewhat smaller wavelength are microwaves. This you're familiar with if you have a microwave oven in your home. These have wavelengths which are approximately a centimeter in size. You can check that these centimeter wavelengths exist if you take, let's say, a little tray of something like, let's say, a cheese or something that melts, and you switch off the rotation of the microwave and you just turn the microwave on, you will find that the cheese has melted in spots, which are the peaks of this microwave in your microwave oven. And these spots are separated by a distance which is approximately a few centimeters. So this is a simple thing to do at home. Please exercise caution. Have someone older around you to make sure that you don't hurt yourself. Somewhat smaller wavelengths are infrared wavelengths. So this is what we perceive as heat from hot objects. Visible wavelengths form a very small part of the electromagnetic spectrum. And then we have higher frequencies or lower wavelengths, which are ultraviolet, X-rays, and finally, gamma rays. And then some of them are benign. They do not lead to any harmful effects like radio or microwave or radar or like visible light. But then the high frequency or low wavelength light, such as X-rays and gamma rays, they can ionize or they can lead to biological damage to cells. So these you have to be very careful about. Of course, any kind of radiation in sufficient quantities is capable of transferring energy, basically heat. So when we say that these wavelengths or these frequencies are not harmful, one must understand it to be not harmful when used correctly. Okay, so this is the big picture of what electromagnetic radiation does. And why have we been talking about light? Because all of modern astronomy, until maybe a couple of years ago or a decade ago, depended on light. All of astronomy is about light. So the different frequencies of light, or you see, there are many pictures here on your screen here. They are pictures of the same object. They are pictures of the Milky Way, our galaxy, but using different kinds of light. So from radio to infrared to optical to X-ray, and then finally gamma rays. And in all these different frequencies, you can see the same object, the Milky Way. And except for the case of optical, the colors that you see are fake. These are what are called false color or pseudo color, where frequency in some range is mapped or represented using frequencies or colors in the optical range, so that you can visually appreciate the diversity of frequencies that are being observed by each of these ways of looking at the Milky Way. So from this, what do we learn? We learn that electromagnetic radiation appears in a wide range of frequencies, and we can use different kinds of instruments to look at astrophysical sources in all of these wavelengths. So there are specific limitations to each of them. There are advantages and disadvantages of using one or the other frequency. Let's not go into that today. It is important to just recognize that there are a variety of different frequencies or wavelengths at which we can observe the universe. And for each of them, there are different sets of instruments. And this is the purview or the field of modern astronomy that uses light or electromagnetic radiation. But now we will switch gears. Okay, this is something that I expect all of you have seen at least once, that the idea that we look at our universe using light and maybe light of different frequencies. But now I want to switch gears, and I want to generalize the notion of what is astronomy. So the definition of astronomy, one would have said, is to detect light using a telescope from a celestial body, so from a star-like or planet-like or some heavenly body in the sky, and use it to learn something. This is what the field of astronomy would be defined operationally. But let's generalize it. Let's ask, can we do something that is similar to astronomy, but without using light necessarily? So let's define astronomy as, we need a messenger. So light could be replaced by something else that can be detected. So instead of a telescope, I could use something else and traced back to its source. This is very important. You cannot do astronomy if you detect something, but you don't know where it came from. So you have to be able to trace it back to its source, and whatever you detect should carry some information. It should tell you something interesting. Okay. All right. So our new definition of astronomy is that we need to detect messengers from some source, be able to trace it back to the source, and be able to extract information from this messenger. And why do we want to do this? We want to do this because there are certain limitations to light. One thing is that for many frequencies of light, there is no way to see behind an object. So suppose, you're standing in front of a wall, you don't know what's going on behind the wall. Okay? We would like, for example, and so you say that, okay, maybe I will use an X-ray, or maybe I will use some other frequency, to find out what is behind some wall. That's one way of going about it. But there are conditions in the universe where no light escapes from certain regions of that universe. So for example, when we look at the sun, the light that we see actually comes from the very outermost layer of the sun. Light from the central regions of the sun cannot escape. So light is constantly scattering inside this star and not able to escape. Only when it reaches the very surface of the star, at that point, it can escape the star. So what we see is just the skin of the sun. We would like to be able to look at the heart of the sun, the core of the sun. And that we cannot do using light. So there are similar other places in the universe which are so dark, or I should rather say so dense, that they trap the light. These are not like black holes that light can never escape. That's a different story. These are just so dense that the light is being scattered constantly and it cannot travel in a straight line. And therefore, we never see light coming from these dense regions. So then we turn our attention to other possible messengers. If not light, then what? And the answer is, well, particle physicists have a view of the world, the universe, which involves many other particles. Light, which is the photon, is only one of these many particles. So we want to ask which of these other particles can be used for astronomy. Turns out that all the particles except the neutrinos, okay, are charged, and charged particles will bend in magnetic fields. So they cannot usually travel along straight lines. So maybe not a great idea to try to do astronomy with charged particles, although it can be done and it's interesting. And I will tell you a little bit about it later. But neutrinos are obviously they're nice particle to use for astronomy because they are completely neutral and they will not be bent by electric or magnetic fields. These other particles, these ones in the red, are either too heavy or they decay or you don't see them in real life. The Higgs boson decays, the quarks are charged, electron, muon, these are all charged particles, difficult to do astronomy with them. The neutrinos are uncharged. Further, the neutrinos are very light. So they have very low masses. We don't know what their masses are still, but we know that they're very small. And therefore, it's very easy to produce them. So things can be produced very easily if they don't cost a lot of energy. And neutrinos, because they don't cost a lot of energy, they can be produced easily in nuclear reactions, for example. And so you're going to produce these neutrinos in stars, let's say, and then these neutrinos will travel along straight lines. So far, so good. Even more importantly, these two things are shared between neutrinos and photons, that they are easily produced and they travel along straight lines. But the beautiful thing about neutrinos is that neutrinos do not interact very much. Unlike light, which scatters off electrons and protons and atoms quite easily, neutrinos tend to just go in straight lines without interacting. They interact, but much less frequently. So therefore, you expect neutrinos to be emitted even from regions of stars, let's say the dense inner part of stars, from which photons cannot escape, but neutrinos can escape. So this is the advantage with neutrinos. Of course, it comes with a disadvantage too, which is that if neutrinos interact less, they will also be harder to detect. Okay? So this brings me to the important point about neutrino astronomy, that if we want to do astronomy with neutrinos, first we have to solve the problem of, can we detect a neutrino? And in fact, this is a problem that the first person who thought about the neutrino already identified, that here is a particle that is very, very difficult to detect. And in fact, very famous scientists, so what you see here on screen, on the right is Hans Bethe, and on the left, Rudolf Peierls. They did a calculation, and then they, based on that calculation, showed that it is therefore absolutely impossible to observe processes of this kind with the neutrinos created in nuclear transformation. So what they're saying, process of this kind is the interaction of a neutrino with something. And then they said there is no practically possible way of observing the neutrino. So this is in 1934, just a few years after the neutrino has been proposed by Pauli. And already people are saying that, well, you can never detect the neutrino. So this is the impossible part of the dream of neutrino astronomy. This turned out to be a spectacularly wrong prediction. So this is also to show that great people, very, very brilliant scientists, often make incorrect, incorrect research, and it's published, and then other people come and correct it. And this is a normal part of doing science, that you say something, turns out that you're not right, and then you correct yourself or somebody else corrects you and you move on. And this is how science happens. So so this is perhaps the only important equation that I will show you. The number of particles that you can see should be thought of as the number arriving per unit area of the detector per unit time, times the cross section, which is an important concept. It is a cross section of each target. In this case, the target is, let's say, proton. And so the area of the proton is what is important here. We have to define this area carefully. It's not really the area of the proton, but something a little bit more sophisticated, which I will not tell you about until the very end. And then it's also proportional to the number of targets and the amount of time that you see. So number of particles is larger if there are larger number of targets like protons in your detector. If you observe for longer, you will see more number of particles. It also depends on how many are arriving. So that's the first factor. And it depends on something intrinsic to the interaction between the neutrino and the target, which is called cross-section. So because the neutrinos have no charge and they don't interact very much, they just simply pass through everything for the most part. So, neutrinos emitted from whichever nuclear reaction, they just travel in straight lines, and they pass through the Earth or your detector basically without interacting, but not quite, not completely, because the number of targets in a detector can be made very large. So you all have learned in chemistry that a mole of any substance has 6 times 10 to the 23 of those molecules or atoms. If you take, let's say, 18 grams of water, that's a mole of water, that already has 10 to the 23 water molecules. Imagine taking a ton of water, 1,000 kilograms of water. It would have many, many more water molecules. And so therefore, in this equation, although your cross-section is very small, maybe you cannot change the flux that is arriving. You don't want to observe for too long. Maybe you want to observe for a month or maybe a year. You don't want to spend 10 centuries doing the experiments. The only thing that you can really change is the number of targets. And that you can change by making just a big detector. And that is precisely what was done. And they actually detected a neutrino in 1956. So they made a big tank, filled it with some liquid, and then the neutrinos that were coming from a nuclear reactor nearby were seen to interact. Okay, so this was the first detection of the neutrino. So, but this is still not astronomy because these are neutrinos coming from a nuclear reactor nearby. Astronomy would involve detecting similar neutrinos from sources in the sky. Or to make it a little bit more general, we will also think of Earth as a neutrino star, because the Earth, because of its radioactivity inside the Earth, also emits neutrinos. So sky and Earth, these emit neutrinos, various energies of neutrinos. On the numerator, on the top here are the energies written in some units. The way to think about it is these are energy measured in the units of mega electron volt. One simple way to think about it is half a mega electron volt is the mass of an electron. Okay, so energies that are smaller than half mega electron volt, the capital M, are lower energy neutrinos, and those that are larger, so 1 to 10 mega electron volts or 100 mega electron volts or giga electron volts. Giga means 10 to the 9, mega is 10 to the 6, and tera is 10 to the 12. So these are all higher energy neutrinos, and they're produced by a variety of sources. So early in the universe, in the Big Bang, neutrinos were produced. These neutrinos were produced with somewhat higher energies at the time, but because the universe has expanded and cooled, these neutrinos now have very low energies. The small m is a milli-electron volt. So 10 power minus 3 times an electron volt, which is like a billion times smaller than the mass of the electron. And then there are neutrinos from the Earth's core due to radioactivity, from the solar core due to nuclear reactions, from explosions of massive stars like supernovae, again because of nuclear reactions there, and finally, due to cosmic rays. So cosmic rays are charged particles created by, let's say, black holes and other astronomical objects very far away. And these charged particles collide amongst themselves and with other particles and create neutrinos in the process. These neutrinos can also be observed, and some of them we see them as what are called atmospheric neutrinos, because the cosmic rays come and hit our atmosphere and make these neutrinos. And there are also cosmic neutrinos because these are neutrinos produced very far away from our galaxy. So there are a variety of neutrinos from different parts of the universe due to a variety of reasons. They have different energies, and so you have to invent interesting ways of detecting these neutrinos. Just like how the different frequencies of light needed different instruments. For a microwave, you have a microwave antenna to detect them or create them or measure them. For radio, you need much bigger dishes. For visible light, our eye works just fine. For gamma rays or X-rays, you need, let's say, these plates to detect. So for different frequencies of light, we needed different instruments. Similarly, for different neutrino energies, we will need different instruments. But if we can observe neutrinos from all these different sources, that would be neutrino astronomy. Okay. Turns out that this dream of neutrino astronomy isn't impossible at all. After the detection of the neutrino in 1956 or so, over the years, we started detecting neutrinos from the sun. So from the mid-60s onwards. From the mid-60s onwards, we also started detecting neutrinos being produced in the atmosphere. In 1987, 23rd February, if I'm not mistaken, a star exploded in the neighborhood of our galaxy. In a large Magellanic Cloud, a star exploded in a supernova, and we saw about 20 neutrinos from that explosion. This is called the supernova 1987A. This nomenclature of supernovae, the way it goes is that in any year, if there is a supernova that is seen by astronomers, they give the name, which is the year, and then the first supernova would be A, and the next one would be B, and so on. After 2005, we started detecting neutrinos also from the Earth's core due to radioactivity inside the Earth. The Earth inside has uranium, thorium, and potassium, which decays via radioactivity and creates neutrinos. And these have also been detected. And very recently, about 7-8 years ago, we started detecting neutrinos from astrophysical sources. So I will tell you in the remaining time a little bit about the detection of these neutrinos from the different parts of the universe, from different astrophysical sources, and what is the future. So what is the future of this very much possible dream of neutrino astronomy? So this is a slightly more scientific way of showing the neutrino astronomy field. On the x-axis or on the horizontal axis is energy in some units, and on the vertical axis is the number of neutrinos that you're seeing per unit area per unit time. And this gray curve here are the neutrinos from the Big Bang. They have not been seen so far. That's why I've put a red cross there. This blue lines are neutrinos from the sun. They have been seen. There's also the neutrinos from the Earth. This geoneutrinos that has been seen. This yellow line here are neutrinos that are created in the atmosphere of Earth. They have been seen. This blue line here are neutrinos, we believe, from astrophysical objects that are at cosmological, very far away distances. They have been seen in the last 5 years or so. And we expect also to see neutrinos from even further away called cosmogenic neutrinos. This flesh-colored line at the very end, these have not yet been seen. So there are still some frontiers of neutrino astronomy that remain unexplored. These are the highest energy neutrinos, so the cosmogenic neutrinos, and the lowest energy neutrinos, just the cosmic neutrino background or the Big Bang neutrinos. Okay, it is difficult to see these neutrinos because the lower energy neutrinos have very small cross section. They don't interact very much, even less than these neutrinos. So it's very hard to measure them. And these neutrinos, the highest energy ones, they interact just fine. The interaction strength is quite good, but their rate of arrival at Earth is extremely small. So there are too few of them coming to us. So we need really, really big detectors to detect these neutrinos, and therefore we haven't detected them yet. So that's the status of the field of neutrino astronomy. So that was basically what I wanted to tell you about today. If there are questions, I can take questions at this point.
Sure.
Or if you would like, I can tell you a little more detail about each one of these sources at this point. So whichever way we want to go.
Okay.
So now I open the floor to you guys.
Yeah, sure. Am I audible to you, Professor Dasgupta?
Yes, you are.
Okay, fine. Because we have just completed about 45 minutes of the scheduled time. So I'll take up certain questions which have been shared by the attendees, although there are plenty of them, as you can see the chat section also. I'll take up the, are there any books translating the work of ancient mathematician like Aryabhatta?
I know of a book by David Mumford, a very famous mathematician, who is also very interested in the work of Indian mathematicians, especially from the Kerala School of Mathematics. He has a very nice book, if I remember correctly, about ancient Indian mathematics.
Okay.
But this is not something that I am an expert on. I'm not a mathematician, and I'm not particularly familiar with what other books might exist.
Okay. Okay. I'll take up the next one. Galileo invented the telescope in 1609. How did he make his invention that popular that lead to future inventions? That's part one. Was his telescope so powerful to see the moons of Jupiter?
Yeah. So the first question was how did he make his invention
popular?
Popular?
Yeah.
That's a very interesting question. Galileo made his invention popular by taking it to the rich people of his country at the time. You know, things have not changed. If you want to get some level of publicity and traction, you have to approach big and powerful people in your community, because they have the reach to take your invention to where it matters. So for example, once he showed his telescopes to the Duke, it became clear that the telescopes could be used to look out for enemy ships coming to their harbor. So that's a useful thing. And these are the kind of reasons because of which Galileo's invention of the telescope became very, very popular. The second question was, could he really have seen the moons of Jupiter? And the answer is yes, of course. That's the whole point. You can actually see Jupiter by eye. You don't need a telescope to see Jupiter itself. You know, on a clear day, if you know where to look, you can see Jupiter by naked eye. But to see the moons of Jupiter, a telescope is particularly helpful. So you don't need that much magnification. I think, okay, I don't want to say something wrong, but I think you need about a 30 times or 100 times magnification in order to see the moons of Jupiter. And that was easily achievable by Galileo's telescope.
Okay, I'll take up the next one. With many super powerful telescopes and astronomical objects, still only 5% of the universe is discovered. Can you explain why?
Okay, that's another fantastic question. It's a little bit off our topic today. So what the question is referring to is that we know that everything that we know and see and understand made of atoms and photons, this only is 5% of the total energy density of the universe. Approximately 25% is something called dark matter, and there's 70% which is called dark energy. So let us not talk about dark energy today, because that's a slightly different topic, but we can talk a little bit about dark matter. So it is not true that we have no idea about the other 95%. We certainly know that 30% of the energy of the universe exists in a form of matter which is not made of atoms as far as we understand, and we call it dark matter. Okay. So we know a little bit about this dark matter because we can measure the gravitational effects of this dark matter. So there are things that are gravitationally lensed by dark matter, stuff moves around this dark matter in the universe in a specific way, and so therefore we know that there is dark matter. Dark energy, we know a little bit about it because we have seen light from far away supernovae, a different kind of supernovae, but supernovae nonetheless. And because of various kinds of astronomical observations, we now know that there is this 30% dark matter and 70%, 25% dark matter and 70% dark energy. What we do not know is what are they made of? So yes and no, we indeed know a little bit about these invisible part of the universe because of our astronomical measurements and cosmological measurements. But yes, on the other hand, we do not know what they're made of.
Okay. I'll take up a few more questions, and I hope you will be sparing another 10 minutes on that. The next one is how difficult it is to detect a neutrino when they interact so less. And second part of that question is that if neutrinos do not interact with other particles and pass through the matter, can we detect the phase, if it is there, of neutrinos?
Can we detect what?
The phase, P-H-A-S-E, phase.
Okay, so let's go step by step. If neutrinos do not interact, how do we detect them? That's the question, first question. Well, neutrinos do interact, but very, very infrequently, very rarely. So that's what I was trying to show you using that equation, that the rate of interaction is very small, but if you increase the number of targets, this is like saying that suppose you have a lot of fish. These fish are very clever. They're swimming in a river, very clever fish. They always escape your net. Let's say they have a chance of escaping, which is 99%. So if you just put one net, the fish escapes. But if you put 1,000 nets, then 1% of 1,000 nets will catch fish, and that's about 10 fish, right? I got that right. Yeah, I'm very bad with actual calculation of numbers, but okay, this one is easy. So you see, it's hard to catch fish. Only 1% of the time you catch fish, but if you put enough number of nets, you still catch fish. Same thing you can do with neutrinos. It's hard to catch a neutrino, but if you put enough number of targets, these protons, which is basically the hydrogens in water, in a big tank of water, you do get some interactions. Can we detect the phase of a neutrino? Indeed. So now you're going a little bit ahead. I did not talk about neutrino oscillations. So each neutrino is actually internally made of 3 neutrinos of different masses or flavors. And the way to think about it is each neutrino is like a clock with hands, and the positions of these hands of the clock tell you relatively how much of each neutrino component is there in the neutrino that you're observing. And indeed, there are ways of measuring the relative phase between these things. But that's something that we don't want to talk about today.
Okay, I'll take up the second last question now. How likely is it for a planet being hit by gamma rays?
How likely is it?
Gamma rays.
To do what?
How likely is it for a planet being hit by a gamma ray?
Planets are being hit by gamma rays all the time. So, there are these things called black holes, and stuff falls into these black holes, creates various kinds of astronomical jets. And in these jets, gamma rays are produced, and there are gamma rays floating around the universe all the time. And these gamma rays are constantly hitting planets and even you, but the rate is small. So that's why we don't worry about them too much.
Okay. I'll take up the last question. Uh, what would happen if two neutrinos collide? Do we expect
Okay.
any radiation or energy transfer?
Okay, this is now, whoever asked this question, you've asked a question that is very close to my heart, because this is exactly what I work on. Unfortunately, this is a long conversation. What happens when neutrinos? No one has measured the collision of two neutrinos until today. Okay, this is something that we believe happens. There's all the reason, mathematically and from the point of view of the physical theories that we know of, to expect that these collisions happen, and they happen in a way that we fully understand, but no one has actually measured it yet. And they happen all the time inside supernovae, inside the cores of supernovae, because there are lots of neutrinos there and they're bumping into each other. Usually, you wouldn't have to worry about neutrino-neutrino collisions because neutrinos are very weakly interacting. I've just told you that. And unless you have a lot of neutrino targets, the first neutrino does not interact with the other one. Okay. So, but there are situations where neutrinos interact with each other, and this is quite interesting. And if you are more interested, get in touch with me and I'll tell you a lot more about it.
Sure, thank you. Okay, so one last question has popped up. How can we make our career in astronomy sciences?
Okay, so full disclaimer, I am not an astronomer. I'm a particle physicist who became more interested in astrophysics. But if I have to give some sort of guidance as to how to approach a career in astronomy, I would say that please study science until 12th grade. Please study physics, chemistry, and mathematics at least. Biology recommended, but not absolutely essential. And then in your undergrad, you would typically do a graduation in physics, although other things are possible, but physics is the most likely choice if you want to do astronomy. And then for your post-graduation, you can go to one of the research institutes or one of the universities which offers courses which are specialized in astronomy, and then maybe you would go on to do a PhD in some area of astronomy or astrophysics. So that's how you would go about it.
Thank you very much, Professor Dasgupta. It has been a wonderful experience having last 45 minutes, and especially you have taken up nearly all possible questions which the attendees have asked, and many of them, they have also written that they would like to hear you once again, maybe maybe on some other advanced topics which you really would like us to know about. And because these students, they are from class 9 to 12, and what I've seen through the feedback form, that some of them are school teachers, some are assistant professors. So I was initially planning for a school outreach program, and that's what I've written to all the speakers also. But now what I'm finding is that this has got some more interesting participants, and that's why perhaps you may have also seen the level of the questions.
It's very high.
It's high.
So you have a very diverse audience, and so I
Absolutely.
try to answer to the best of my ability. I apologize if my answers were sometimes not as advanced as you were expecting, because I don't know who you are.
Yes,
and
exactly.
I don't know exactly at what level to pitch my answer.
Exactly. So I also,
please forgive me.
I also would like to apologize to all the attendees, because I was not exactly thinking that it will go to this level. So, but in any case, their participation, their inquisitiveness, I hope it must have been satisfied by the speaker, and hope to see you all again in another interesting program which we are going to organize on August 31st, Ethics in Science. And thank you very much, Professor Dasgupta. And if possible, would like to engage with you again, maybe sometime at a later date when you'll be again free in that case. Thank you. Thank you very much.
Thank you so much. It's a pleasure.
Okay.
Thanks a lot.
Fine. I request all the participants to kindly fill up the feedback form.